We're going to have a quick class today. There's a lot to cover, so I'll probably not be asking too many questions. If you want to identify who my TAs are, they're the ones with the hats and the masks. Anyway, you should have brought your own costumes, right? Let's begin. We're going to look at, in today's class and the next class, we're going to look at sequence-to-sequence models, which convert sequences, one input sequence to a different sequence. Today, in particular, we're going to be looking at the Connectionist Temporal classification model. So here's the sequence-to-sequence modeling problem. You have a sequence X going in and a different sequence, oh my, Y coming out, like in speech recognition. Speech goes in and a word sequence comes out. Or maybe it can be a character sequence or a phoneme sequence. Or in machine translation, a word sequence goes in, a different word sequence comes out. Dialogue systems. Somebody says something, out pops a completely different sequence of words. Question answering. Question comes in, answer goes out. Now, in general, you cannot assume that the number of symbols going in, inputs going in, is the same as the number of symbols coming out. So there are two different settings over here. The first is one where you have order synchrony. So for example, the first problem there, speech goes in, the recognition output comes out, I eat an apple. Now here there is a correspondence between the output and the input, but it's not one-to-one. So the first portion of the recording corresponds to the word I. The subsequent portion of the speech corresponds to the word ate. The third portion corresponds to an. The fourth portion corresponds to apple. So there's an order correspondence. On the other hand, if you look at the second problem, I ate an apple, which gets translated to Ishaba and an Apfel gegessen. The order of words and the output, the number of words in the output is actually greater than the number of words in the input. There is no strict one-to-one correspondence between the output and the input. In fact, if you look at the order, I became ish, which is fine. The first one became the first one here. But ate actually split into two words, habe gegessen. So you can see that the kind of synchrony we're used to seeing doesn't exist anymore. Today we're going to be focusing on the first problem, the problem type, which is what we began discussing in the last class. So this is the problem. The input and output sequence happen in the same order, but they may not be time synchronous. However, they can be aligned to one another because each the input occurs in the same order as the output. And there are two problems over here. First is, how do we perform inference on such a model? Namely, if I actually give you the input, how do you predict the output? And secondly, how do we train these models? So here's our first question for the day. We actually saw a partial answer for, I'm not sure what's going on here. We saw a partial answer for the first problem, who is number 37. Okay. What was the partial answer for the first problem that we saw in the last class? Okay, who's 32? Yes. So could you repeat that, please? We are trying to find the optimal path, but the solution, partial solution we actually saw us finding a greedy solution where we picked the most likely symbol at each time and just tried to squish those together, and we found that was a suboptimal thing to be doing because you cannot distinguish between repetitions. Moreover, it only gives you the most likely time synchronous output, which is not necessarily not the most likely order synchronous output. So anyway, for now, we'll assume that this is partially solved. The second question is, how do you train such models? And then once again, we saw that if we were given training data where you had the inputs and the order aligned outputs with the timestamps, namely if you were told that the first symbol occurred at time 2, the second one occurred at time 4, the third one occurred at 6, the fourth occurred at 9, then it was easy enough to compute a divergence. The first thing you would do was just to convert this order synchronous output to a time synchronous output by repeating symbols. And then subsequently, we could just compute. Now we have a time synchronous output. We could define a divergence function, which was the sum of the divergences at the individual times. And then again, who is 33? Where is my, do I have chalk here? Yeah. Who's number 33? Yes. So if I have a sequence of, if I have a symbol, if I'm representing classes in a one-hot manner, and my network outputs a probability over all of the symbols, then what is the KL divergence between the output and the desired output? So we just saw that if I have any symbol, if I have a target symbol C, and YC is the probability assigned to the target symbol by the network, then the KL divergence that we defined was between the KL divergence between Y and D was simply minus log YC, correct? Now if I have a time synchronous output where I have one output symbol for every time instant, what I really have is a sequence of symbols, right? And so if I have a network which is producing outputs, I have inputs x1, x2, x3, and so on. Each of these goes through my net, and at each time you actually get a probability distribution over all of the symbols. And if you have a target symbol sequence which is, say, let me call this, S1, S2, S3, then what would the sum of the Kullback-Leibler divergences at the various times be? That is simply going to be the negative of the log of the probability assigned to these symbols by the network at each time. So the overall KL divergence between the output sequence and the target sequence is going to be minus summation over T log of the probability assigned to the Th symbol. Everybody clear about this? It's making sense, right? And so keep this in mind. We're going to use this quite a lot, this particular equation over here. And now if I actually compute the derivative with respect to the output, oh, okay, so who is 29? When I compute the derivative of the divergence for back propagation, how do I actually compute the derivatives? Can you tell me which derivatives I would need as the first step for back propagation? Anybody else? Who is 34? Yes. What is the derivative that I need when I'm performing back propagation? Something much simpler than that, right? So maybe Mr. 35 can tell me. Who's 35? Someone's 35, yes.
So are you asking for like the first derivative that you want?
Yes.
Like, I mean, with respect to the divergence first.
Yes. So what would the derivative you're computing be? Okay, let me answer you guys. Maybe the question is not clear. As a very, very first step, you need the derivative of the divergence with respect to the output of the network, right? Which means that at each time, at any time t, you need the derivative of the divergence with respect to yt. And we know that the divergence with respect to yt depends on, how many symbols does it depend on, Mr. 27? How many terms does the divergence depend on at each time? Okay, I'll answer you. My questions are maybe not clear. At each time, we just saw that the divergence itself is just the negative log of the probability assigned to the target symbol, right? So will there be a derivative? What will the derivative of the divergence be with respect to the non-target symbols? Probably 0, because they don't even figure in the equation, right? So you're going to find that the derivative of the divergence with respect to yt is going to be 0 everywhere, except for the tth symbol, where it's going to be -1 over the probability assigned to the tth symbol. So far, so good. But then, if only the output order synchronous but unaligned symbol sequence is given to you, then clearly you cannot perform this computation. So what is missing? Who's 1? Yes, what is missing?
The number of repetitions.
So you don't know the number of repetitions of each symbol, right? Therefore, we don't even know which symbols to use at each time in order to compute this divergence. So who is 30? How did we solve this problem in the last class? Okay. Who is 2? How did we solve this in the last class? You're 2? Yeah. We guessed the alignment, right? At each step, we sort of came up with a guess, which said maybe this was what the timestamps were. This was how many times we had to repeat each symbol in order to align it time synchronously with the input. And this guess, was this guess going to be the perfect the first time around? Who's 28? Yes. So how did we fix that? The Viterbi is still just, what was the Viterbi doing?
So for any given input position, it picks the...
Yeah, you're giving me the procedure, but what was the point of the Viterbi?
To find the best sequence.
Define best.
Most probable.
Most probable. Is that dependent on the model parameters?
To the extent that the output probabilities are.
The output probabilities are dependent on the model parameters. Therefore, the alignment that you get is going to be dependent on the model parameters, right? Given this, who is 9? Okay. Is the alignment you get at the beginning of the training going to be okay? Why not? The model parameters are not properly computed, correct? In the beginning, the model parameters are all noise, so the alignment you get is going to be poor. But then you're going to align with it anyhow, and then you're going to use that to train your model. Hopefully the model is better because you got some things right, or if you use a large enough amount of data. And then you use the updated models to go back and re-estimate how to align these unaligned symbol sequences with your input, and then retrain your models and repeat the process until the whole thing converges, right? Now, who is 11? What was the problem with this setup? What can go wrong here? We mentioned this towards the end of class. Yes, I know that's a procedure, but what can go wrong? Okay, unlucky 13. Who's unlucky 13? Okay, what can go wrong?
We don't know how many times of each.
Right, but you're trying to guess it, right? So why would your guess be bad? Yeah. It depends on the initial models. So if your initial models are bad, the initial alignments you get are going to be poor. Because the alignments are poor, the next update is going to be bad. You're going to end up being stuck in a poor local optimum. Let me pin that. How much time? Oh, to time the pole. Okay, guys, time's up. Right? Let's move on. Viterbi training explicitly estimates the alignment of each training instance and computes the divergence for the estimated alignment. This is true. It requires re-estimation of the alignments in each iteration because you're going to estimate some initial alignments, update your models, use that models to go back and re-estimate your alignments, right? So it ends up being quite computationally intensive. And more importantly, the approach heavily depends on the initial alignment that you assign when you initialize your models. And so if that is bad, and it will usually be bad because you're going to get it wrong the first time around, this is going to go into a poor local minimum. So why do we need to commit to one alignment? Here's the alternative. Let's consider every single possible alignment when we're training the model. So what exactly do we mean by considering all possible alignments? First, remember what we did? To compute the alignment, we sort of pulled out the rows corresponding to the probabilities of the symbols in the target sequence and created a separate table. And then we created a graph from it and pulled out the most likely path from this graph where the probabilities for each of the symbols have been derived have been computed by the model. And of course, the divergence that we computed was the sum of the negative log probabilities of all the symbols in the best path. This is your best guess for the actual divergence of the best alignment, right? Now, here's what actually happened. How many paths are there? Who's 14? So how many paths would you have from the first node to the end in this graph? It's going to be a very large number, whatever it is, right? Will each of them have the same probability? No, right? So what are we doing over here when we perform Viterbi alignment? Which of those paths are we choosing? We're only choosing, so we have a great many different alignments. Let me call them A1, A2, A3, A4, A5. These are all the alignments. Each alignment has a probability which is simply the product of the probabilities along the path, right? And all we did, okay, here's another question for you. Who's 26? If I simply assign the probabilities to each of these paths as the product of the probabilities of all the symbols along the path, will the probabilities of assigned to all alignments sum to 1? Why not? Let's just take your word for it. The answer is no. Why? because you're only looking at a subset of all of the probabilities output by the network. So you're going to be looking at some subset of all possible ways of generating output sequences, right? So now if I want to convert this set of probabilities to an actual probability distribution over the paths, 15, who's 15? What would I do? If I have a probability as computed for every alignment from the graph, I just normalize it. I can just divide by the sum of all of these probabilities, and now I have an actual probability distribution, right? This is going to be key. Now, when I pick the most likely probable alignment, all I'm doing is picking the one alignment that has the highest probability. This is committing me to what could potentially be a really bad alignment because my model was bad and the probabilities computed were really bad. So maybe picking the most likely alignment as given by my current model is an improper thing to do because it's wrong and it drives me into a local optimum. So who is 16? Can you suggest a solution? Okay. Pardon me?
Instead of changing our alignment gap, we just fix one.
Even if you fix one, it's going to be wrong, right? Who is 41? Yes, can you suggest something else? You can try a lot of different paths. So who's 17? If you were trying a lot of different paths, would you give them all the same importance? You wouldn't actually give them all the same importance. If you trust your model even a little bit, you're going to give more importance to the ones that have been assigned more probability, but you're not going to just pick the one most probable one. So one good suggestion would be to randomly sample from that distribution, which might be something better than just picking the most likely one. If your model is perfect, the random sample is going to give you the most likely alignment anyway, right? That is not a bad thing to do. Why don't we instead average over all possible alignments? So what we want to do instead is do this. Every single alignment is a sequence of symbols. The divergence computed from the alignment is the negative of the sums of the logs of the probabilities assigned to the symbols in that alignment. And what we really want to do is compute the average. So this E over here is the expectation term. And so what we would do is say the probability sum over all alignments, the probability of the alignment given the input x, because obviously the probabilities are computed using the input, and given the target symbol sequence, because obviously which sequence of characters you give, symbols you output depends on the target symbol sequence, times the divergence for that alignment. This is what we would be doing. So this equation over here is simply saying I'm going to be computing the average of all of the divergences computed across all alignments. Is that making sense to you guys? Now, this expectation operator, it turns out, is linear. So who is 18? When I say the expectation is linear, how would that affect us here? You're right. First, your answer was right. This looks good. Yes. You're supposed to wear your masks. Wear it above your glasses. Yes. माथे पे पहन लो. ऐसे. Time's up, guys. Okay. So the training without alignment procedure computes the average divergence over all possible alignments. This is true. This means you don't need to explicitly compute the alignment in each training instance. You're evaluating all possible, averaging over all possible alignments. And now, this is the divergence. The expected divergence is what we wanted to minimize. But as was rightly pointed out, the expectation is a linear operator. So instead of saying the expectation of the negative sum of the log probabilities assigned to the symbol in the sequence, I can move the expectation inside the summation, and I'm going to end up with the negative sum over all time of the expected log likelihood of the symbols that are possible at that time. Now what this means is that at each time, take this example over here. Take time 4. There are 4 symbols possible at time 4. There are actually 3, but one of them is repeated, right? Each one of those 4 has a log probability assigned by the network. So the first one on top has y4b. That is the probability assigned by the network to the symbol at time 4. The second one has y4e, which is the probability assigned to e at time 4 by the network, and so on. So each of the 4 has a different log probability. But then, if you consider the input sequence, each of those 4 nodes in the graph has a different probability of appearing in the actual alignment, right? If I chose a random alignment from this graph, what is the probability that the random alignment would include y4b? It is some value, and you're going to have one of a probability of that kind for each entry in the column. And so what this equation is telling me is that all I need to do is to sum over all time. At each time, I go over the column, and over the column, I'm going to be multiplying the log probability assigned to the node. Every node in the column, I'm going to be multiplying it by the probability that a random alignment will actually go through that node. That making sense to everybody? Right? So this first term is the probability that if I choose a random alignment from this graph, that random alignment is actually going to go through the node. So the key here, this term has already been given to you by the network. So the thing that's missing is the second term. This is what we need to compute from the output of the network. That's what we need to compute as part of this training process. So what is that term? So take this y3e. What we are looking for at time 3 is the probability that a randomly chosen path is going to go through each of the nodes. So if I specifically consider the node y3e, which is highlighted in the middle, it is the probability that I'm going to choose a path from the portion of the graph that goes through the node. That's the only way a randomly chosen path is going to go through that node. That's highlighted, right? So what is the probability that a randomly chosen path is going to go through that node? It's going to be the total proportional to the total probability of the subgraph that I have just shown, which forcibly goes through y3e at time 3. Is that making sense? Right, raise your hands if it is. Right? I just need to know. Making sense? Okay. So the probability of this graph is proportional to, why am I saying proportional to? Who's 20? Who's 20? Somebody's 20. Okay. Why am I saying proportional to? So I'm saying that the probability that a randomly chosen path is going to go through the node is proportional to the total probability of the highlighted region of the graph. Why am I using the term proportional to? Yeah?
Because you're multiplying all the probabilities to get to get the total alignment probability, you're doing multiplication of the entire thing, right?
So that's not quite it. Yeah.
They're not like normalized, right?
Pardon me?
All the probabilities like to be like exactly like dividing all of the same term.
So there's you guys actually answered me earlier. If the total raw probabilities of all the alignments in the graph doesn't sum to 1, right? So if I took basically the total probability of this entire graph, all paths through this graph doesn't sum to 1, which means that I would have to normalize everything to make them sum to 1 before that. In the absence of normalization, the total probability of the subgraph is going to be proportional to the probability of randomly choosing an alignment that goes through the node, but it's not going to be exactly equal to it. We'll hang on to that thought as well. So for now, our problem is to find the total probability of the subgraph that is shown, where the subgraph goes through the node y3e. This total probability is going to be proportional to the probability that a randomly chosen alignment will include the symbol E at time 3. That making sense? Right? So this is what I need to compute, and that the probability of that subgraph can now be decomposed into 2. Is the probability of the subgraph starting from the beginning that goes into that node. Now the graph itself has 2 parts. It's a portion of the graph that's leading into the node and the portion of the graph that's going out of the node till the end. So the total probability of the subgraph is going to be the probability of the region of the graph that's going into the node times the probability of the subgraph that's going out of the node to the end, conditioned on the first portion of the subgraph. Why is this conditioned? Because we know that any time I have something of this kind, I have A, B, C, D, E. If I want to decompose this, this is going to be P of ABC times P of DE given ABC. This is simple Bayes rule, correct? So which means that the portion of the probability of the red portion of the graph conditioned on the blue portion of the graph times the probability of the blue portion of the graph is going to be the probability of the entire subgraph shown. Now here's where we make an extra discovery, that I don't need to condition things at all. And this has to do with the fact that when you actually, the process of selecting an alignment is the process of choosing one entry each from these probability distributions, right? But the probability distribution computed at this time does not depend on the actual value that I choose. The probability distribution that I compute at this time does not depend on which value I choose at this time, because these distributions are already given to me. If I'm given an input, the input has been processed by the network. After having processed by the network, I have a probability distribution at each time. So these things are already given. So if I randomly chose this entry over here, this does not affect the probability that I will choose this entry out here. Is that making sense? Right? So what this means is that the symbol that I will choose at any time is independent of the symbol that I will choose at the next time, given the input. Now, under what condition would this assumption break? Under what condition would the assumption that the symbol I pick over here break? Go ahead.
No, I have a question. Can we always choose like completely independent ones if we're constrained to pick either
So if you're going to, is there anything in this model that imposes that constraint? That's basically all we're saying over here, right? If I want to make this probability, the probability of choosing a symbol here depend on the symbol I choose over here, how would I do that? That's still not within the model. The way I would do it is to have that go back as an input here. Only then will the symbol I choose at any time modify the probability distribution I get at the next time, and then I'm going to get dependence, right? Here, as far as the model is concerned, there is no dependence. The constraints are external. So what that means for us over here is that the probability of randomly choosing an alignment from the blue portion of the subgraph is independent of which alignment I choose from the red portion of the subgraph, right? It doesn't say you can't, if I choose a different alignment from the red portion, that's not going to modify which particular path I choose through the blue portion of the subgraph. And so the total probability of the entire subgraph can be decomposed into two parts. That is the probability of the red portion of the subgraph, which I will call alpha TR. So what is alpha TR? Alpha TR is the total probability of a subgraph that starts at the origin and ends at the rth symbol at time t, times the second term over here, which is the probability of the blue portion of the subgraph, which I will represent as beta TR, which is the probability of the subgraph that follows the node representing the rth symbol at time t. So are alpha and beta making sense to you guys? Right? So if they are, raise your hands. Pretty much everything else is going to follow this. I'm not going to be following the math on the slides. That's for your reference. The concepts are very simple to understand. And so we need to compute alpha TR and beta TR. Let's see how we'll do that. Let's focus on alpha TR. Alpha TR is the total probability of the subgraph shown. It is the total probability of all paths that lead from the source node to the TRth node in the graph. Now, how can I decompose this? Look at alpha TR. Now, there are only two ways of arriving at y3e, right? Arriving at the symbol e at time 3. And the two ways are highlighted by the red and the green node in the top figure. So the only way you can arrive at that particular destination node is to either go through y2b or go through y2e, correct? So that means the total probability of arriving at y3e, meaning at e at time 3, is going to be the probability of arriving at y2b and then extending it to y3e, or that is plus the probability of arriving at y2e and then extending it to our target node. So this in turn means that the total probability of the subgraph from the source to this destination is the total probability of the subgraph until this node times y2e plus the total probability of this subgraph ending at this green node times y3, right? Is that decomposition making sense? It's fairly straightforward, right? What is the total probability of the subgraph ending here? Who is number 21? What would that be? So symbolically, in terms of alphas and betas, what is it going to be? Okay, I'll answer. Maybe that's not clear. This is just, that guy here is simply just alpha 2b, right? Similarly, this guy over here is just alpha 2e. And so I can just write this like so. This total probability of the subgraph starting from y0b and ending at y3e is going to be alpha 2b times y3e plus alpha 2e times y3e. You can see how this works out, correct? Or more generally, If I have a whole bunch of these guys, then the total probability at any node for any TR is going to be the sum over all of the parents of that node, all the predecessors of that node, of the product of the alpha for the parent times the current node probability. That making sense to everyone? Right. Okay, so here's the general rule. I can say alpha TR is simply the sum over all of the parents. So specifically, the parent for any node is simply going to be the set of rows to which can lead into the node, correct? So the rth node over here can only be led, the rth row can only be led into from another node also in the rth row or from a node from the previous row. That's how the graph has been drawn. Meaning to get into any node, I can either travel horizontally or I can go one step down. So there are two predecessors. One is in the same row at the previous time. One is in the earlier row at the previous time. So you can go through those parents, and the term you would be adding is the alpha term at the parent times the current symbol probability. Let's apply this specific rule to this graph. What you're going to find is alpha TR is going to be the sum of the alphas at the two blue nodes, alpha T minus 1R plus alpha T minus 1R, R minus 1R is basically the row index, times YT, the probability assigned to the symbol in the rth row at time t. That's YTSR. There's a lot of math over here, funky looking math, but there's nothing particularly complicated. It's very straightforward, right? So what we have done is to define this alpha term at any row, for any symbol in any column in terms of the alphas in the previous column. So this obviously leads us to a very nice looking dynamic programming algorithm who's 38. So how can I use this, Audrey? You can start at the beginning and simply step your way forward, right? So what I would do is have this. In the very first column, I can define the alphas for all of the nodes. I know that I'm not allowed to be in any except the first node at time 1. So alpha 0, 0 is simply going to be the probability assigned to the symbol in the first symbol at time 0. And the alpha terms for the rest of the first column are going to be 0. And then subsequently, I can just step through the net. And at each time, I can simply sum the alphas over the parents and multiply that by the current symbol probability. So I'd go down from the top row all the way to the bottom. I just work my way down the column and compute the alphas for every node in the column. Now, in the specific,
So just want to make sure, it's the alpha same as the best score from the previous?
The alpha is the total probability of all paths from the source to that node. Right, that's what we are using here. The alpha is going to be the total probability of all paths from 0B to 3E in this case. The entire graph. It's not the best, right? Which is why you're summing, you're not picking the max. So this portion is very straightforward. There's nothing particularly complicated over here. And now I can use this and I can compute the alphas for the second column and the third and the fourth and the fifth. At each time, I'm going to be computing the alphas for all the nodes in the column based on the alphas for the previous column. I'm not going through the math. Go through the slides. The concept is very simple. You can code it, right? And now, here's the bet. What is the total probability of all the nodes, all the paths through the graph from the top left corner to the bottom right corner? Who's 23? What's it going to be? So, but what would that be in terms of symbols we've got? It's going to be alpha 8e. That's this alpha term, right? The alpha at the very end is going to be Wait, we have two 23s? Doesn't matter. Okay. Can you put this on? It's fallen off. Thank you. So the alpha at the bottom right corner is the total probability of all paths through the graph. But now we have figured out how to compute this first term, which we will call the forward probability, because you're computing this forward from the end to any node, right? We have the second term to compute, which is the probabilities for the blue graph. And guess what? This can be done the same way. This is, I'm just going to replace the total probability of that subgraph, the first portion with alpha r out here on the slide. But then let's look at how we can compute the total probability of the blue graph, which is the second term in the complete graph. Now that is the probability of this portion of the subgraph, which is the total probability of all paths starting from the orange node but not including the orange node. 22, who's 22? Why am I not including the orange node?
Because you have computed the orange node in the alpha.
I have already included the orange node in the forward pass, right? So all I need to do is to compute the rest, total probability of the rest of the path. Now who is 24? Can you tell me how I can decompose this the same way that we did for the forward?
I mean, it's all the same constraints, right? So like each probability at t plus 1 times the multiplied by the 1 before, right?
Right, but then remember how we did this in terms of recursively in terms of alphas. Do you see a similar symmetric structure here?
Yeah, I mean, starting from, if you go from backwards, like from A.
I'm just looking for this particular node, so maybe 25. Do you see a symmetric structure here?
Yeah, so if you consider that beta t plus 1.
Okay, so I think some of you know a little too much, so you can't answer the simple questions. But this is really what it is, right? The total probability of the entire subgraph starting from the orange node is going to be the sum over all the nodes that can follow the orange node of the total probability of the subgraph starting from that node to the end. So the total probability of the subgraph shown is going to be the total probability of the subgraph starting from the green node going to the end plus the total probability of the subgraph starting from the red node going to the end. This clear? Right? And who is 31? What is this term over here? Thank you, right? That's going to be, I can just pull y4 out, and now this begins to look very similar to what we just saw. And so this is going to be, the total probability of this guy here is going to be y4f times beta y4f, beta 42, and the total probability of this subgraph is going to be y4e times beta 41. Making sense to everybody? Right? It's very straightforward. So I can generally write the beta term at TR as the y at the y4e times beta 41 plus y4f times beta 42, or generally beta TR is going to be the beta term in the same row at the next time. So that's going to be beta t plus 1r times the probability of the symbol in the same row at the next time, which is yt plus 1 sr, right? Plus the beta term for the next for the next row at the next time, which is beta t plus 1 r plus 1 times the probability of the symbol at t plus 1 in the r plus 1th row. Yeah. the beta is the probability that a randomly chosen alignment is going to lie within the white portion of the graph. A randomly chosen alignment for the rest of the sequence. Okay? Or more generally, I can say beta TR is the sum over all successors of R, which is to say, now in any particular row, you can either continue in the same row or go to the next row, right? So it's going to be the sum over all the rows that can succeed the rth row of the beta term for that row at the next time times the probability of the symbol in that row at that time. So it's the sum over all successors of beta t plus 1q times yt plus 1 sq. Now this is just math. Reading out math is very pointless in classes, I know, but I think the concept here has to be very straightforward, right? So here's what we did. We have defined the beta term at each time in terms of the beta at any position at any time in terms of the betas in the next column. And this gives us our setup. I know that the probability of the graph, that the graph ends only at the bottom right corner. So the beta for the bottom right node is going to be 1. For the rest of them, it's going to be 0 in the final column. Subsequently, I can just work my way back, and for each column going backwards, for each node, I can work my way up the graph. I can sum over all of the nodes that can follow that node, all of the possible successors. And for each successor, I'm just going to be adding the product of the beta for that successor and the node probability for that successor. It's a very simple operation. And so I can compute the betas for the first column going back, the second to last column, and the third and the fourth. I can work my way all the way back to the beginning. And now my problem is solved. If I want the total probability of this subgraph, the probability of the orange subgraph was alpha TR. The probability of the blue subgraph was beta TR. So the total probability of the subgraph that went through the TR node is simply alpha TR times beta TR. So in other words, the total probability that a random alignment is going to go through the rth row of the tth column is simply going to be the product of the alpha and beta t terms at that position. And now, if I sum up the alpha TRs and the beta TRs, the product of alpha and beta over a column, is that going to be 1? Anybody? Who's 40? Is that going to be 1? Again, not, because basically you're saying what is the probability that the product of alpha and beta is simply the probability that a randomly chosen alignment is going to go through that node, right? If you sum it over the entire column, that's going to be the total probability of all possible alignments through this subgraph, because it has to go through one of those rows, one of those nodes. But we know that the total probability of the graph is not 1, because this is just a subset of all possible symbol sequences that you can generate from the network output. So if you want to compute the total probability that an alignment of the given input includes the rth symbol at the tth time. So if I want to compute the a posteriori probability that an arbitrarily chosen alignment, a randomly chosen alignment of Beefy, my horrible example in this case, to the input will go through the symbol E at time 3, what I really need to do is to normalize the product of alphas and betas over the entire column and choose the normalized value for the node at that time. That making sense? Right? All of you are falling asleep somewhere anyway.
Question. What is capital S in this?
Pardon me?
What is
What is?
Capital S, the folder guy.
This one, this block S? This guy?
Yeah.
That is the B phi over here. That is the unaligned sequence that you've been given. Right? That's what you're trying to align. So anyway, the mechanics of it is that for every node in the graph, you can compute this gamma term, which tells you what is the posterior probability that a randomly chosen path through the graph is going to go through TR, which is the posterior probability that an alignment of the input to the unaligned sequence that you've been given as part of the training will include the rth symbol at time t. And now that you have computed that, all of that rigmarole was just to be able to compute this term over here, which is the expected divergence in the tth time instant. You're going to sum that across all time, and this is going to give you the total expected divergence over all possible alignments of the input to your label sequence. And now once you've done that, we'll skip the poll. Take a look at the poll. So here's what it is. The forward-backward algorithm is used to compute the a posteriori probability of aligning each symbol in the compressed sequence to the input. These probabilities are required to compute the expected divergence across all alignments of the compressed symbol sequence to the input, because that's what we really want to compute, right? And subsequently, once we have computed this guy, if you want to compute the derivative of the divergence with respect to the output of the network at any time t, we just need to compute the derivative of this term. And you just have to choose the one column representing the specific time t, right? So we just need to be able to compute this derivative from this term here. And that derivative, of course, is very easy. Okay. Again, observe that this is just, it's actually not easy. It's the derivative of gamma TR times log of y TSR. Obviously, y is a function of the network parameters, but then gamma also is a function of network parameters because gamma has been computed from the probabilities assigned to the symbols by the network, right? And so there's another term. Observe that if I want to compute the derivative with respect to the probability assigned to the symbol E at, say, time 2, then the symbol E has occurred in 2 rows of my table. So I would be summing this guy here across both rows to get the contribution of the symbol E to the total divergence. And so when I compute the derivative, all I'm really doing is, remember, this row vector represents the derivative of the divergence with respect to the probabilities assigned to each of my symbols, right? So for any specific symbol, I'll just sum over all the rows in my table that include that symbol, and the term I'm summing is going to be the derivative of the product of gamma and the log probability assigned to the symbol at that in the node. And so in this case, for example, if I want, say, the derivative with respect to E, I would have to sum this term, the derivative of the product of gamma and log y over both nodes. So far so good. This term is the one that we really need to compute, the derivative of the product of gamma and log y. Chain rule, we know that, I know this is standard rules of derivatives, we know that is simply going to be gamma over yt plus the derivative of gamma times log yt. And it turns out this second term is really ugly to compute because gamma is a very complicated function. We've included the entire network. Whenever you run into something, yes?
What is the reason that why we need to sum between YE and between those?
So basically what we want over here is I am computing the derivative of the divergence with respect to the output of the network, right? So each term is the derivative of the divergence with respect to the probability assigned to one symbol by the network. And over here, the symbol E has occurred twice. So each of those is going to influence my divergence. That's why. Anyway, so here's the crazy bit. This term is really ugly to compute. So we do what engineers do. We throw it away. And we say, I'm just going to use this first term, and I'm going to come up with a crazy explanation for why it's okay to do so. And I'll say, you know what, I'm not learning anything discriminative, I'm performing maximum likelihood estimation. And that works. And once we do that, this whole thing becomes really, really simple. Observe what has happened. All that happened is the ratio of gamma and the probability assigned to the symbol by the network. And once you simplify things, this entire derivative term becomes very simple. You have a forward-backward algorithm to compute the gammas. The derivative of the divergence with respect to the probability assigned to any symbol at any time t is simply going to be the negative of the sum over all rows of my table that include that symbol of the gamma, which is basically the total posterior probability of that symbol appearing in the alignment, times minus 1 over the probability assigned to the symbol by the network at time t. And so that can now be plugged in to your divergence formula over here. So it's a lot of complicated looking explanation, but at the end of the day, it comes down to this. That if you're given an input and output sequence without an alignment, input and output sequences without alignment, and if we want to train the models, here's what we do. We set up the network, typically a many-layer LSTM. We initialize all the parameters of the network. Then in the forward pass, for each training instance, you compute this entire probability table. Then you generate the reduced table, the graph, representing the symbol sequence for that training instance. Then you can just perform the forward algorithm and the backward algorithm to compute alpha and beta for every node in the graph. And from those, you can compute the gamma terms, as we just saw. And we can now use the gamma terms to just compute the derivative of the divergence with respect to the output of the network, every output of the network at every time. And that's going to give you the gradient of the divergence with respect to the output of the network at each time. And those can be back propagated through the network. So this is the derivative of the divergence with respect to the output of the network at each time. And those can be back propagated through the network. So here's the story so far. Sequence-to-sequence networks which irregularly output symbols can be decoded using Viterbi decoding, which assumes that a symbol is output at each time and then merges adjacent symbols. Wasn't a great idea. We'll return to that. They require alignment of the output to the symbol sequence for training. Training can be performed by iteratively estimating the alignment by Viterbi decoding, and time synchronous training, or alternately, you can simply train by optimizing the expected divergence over all possible alignments. And that is going to be more optimal because you're less likely to get stuck in local optimum. But then we're not done. There's one final issue to deal with, which is this business of compression. So let's say I used my greedy decode, and my greedy decode gave me this time-aligned sequence of outputs. To get the order-aligned representation, I must compress this, right? It isn't clear from this whether the compression is the word read or the word read. Both of them are plausible. Both of them are in the dictionary, right? So this is basically just an instance of what we saw earlier. And so how can we deal with this? To deal with this, we are going to introduce a do-nothing symbol. A do-nothing symbol is basically a symbol which says nothing happened here. Now, typically, when a network is outputting stuff, you get outputs of this kind. E, 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 B, B, B maybe. So what this is telling you is that you're ramping up towards terminating an E, then you're ramping up towards terminating a B, right? I can also introduce these dummy symbols, nothing happened here symbols, meaning at these regions there's nothing of interest happening. And now I'm beginning to terminate an E, right? So then when the last E happens, that's where it terminated. Now I'm beginning to terminate a B. And when it ends, the B ended. And then nothing happened here. And then I see another B again. And now here, another B ended. So when you say nothing happens, the nothing happens after the dramatic event, which means whatever preceded the blank symbol represented a transition, something pretty dramatic. So the only job of the blank symbol is to serve as a separator between repetitions of a symbol. So for example, if you look at that first time-aligned decode, 3 R's, 3 blanks, 2 E's, 3 blanks, 3 D's, that's going to compress to red. The second one, 2 R's, E, 2 E's, D, observe that one E ended, then you saw the blanks again, then there was a second E. So that's actually a read. The third one, it was 2 R's, then there was a blank, then an R started again. Every time a blank interrupts, something new starts. So that actually ends up being decoded to 2 R's, and E, and 2 D's. And who is number 39? Can you tell me what that fourth guy is going to be? That's correct, right? That's what it's going to be, 3 R's, 2 E's, and 3 D's. So you see how the blank works. I'll skip this poll again. But here again, which of the following are valid expansions of the character Billy? Only the last one is a valid character of expansion of Billy, as you can see. Because the rest of them are going to lose a character. There are 2 L's, right? Or have some repetition. Anyway, so if I'm going to introduce this extra do-nothing character, I have eliminated the problem of dealing with repetitions, but then it changes things a little bit. And the way it changes things is that now my symbol vocabulary that the network can output includes the blank. I have to account for the blank. So the network output now has, for example, if I was recognizing characters in the alphabet, I would now have a 27th symbol, which is the blank. And so at any time, the network is actually going to output probabilities not just for the symbols in your vocabulary, but also for the blank. And furthermore, take a look. If I were to just perform a greedy decode, it naturally separates out repetitions. So this, for example, is, what is this? What would this one be? Who is number 19? Yes, what would this be? It's just the answers up there. 2 B's, they compress to a single B. There's no separator. 2 E's also compress to a single E. 4 F's compressed to a single F, and then an E. So this is just B phi, right? I hate this example. You'll see why. What about this guy? Who is number 10? What is this going to be? It's going to be B followed by an E because there are repetitions of E, right? Then the blank occurs between the E and the F, so it's not really doing anything. Then it's an F again and an E, so it's still B phi, right? Now, what about this one, number 3? Who is number 3? Yes, what is this going to be? Thank you, but how many F's? 2 F's, because there's a blank between the 2 F's. So you can see how this works, right? Now, the introduction of this blank makes things a little complex. Observe that a blank may or may not appear between two distinct characters. So here I have beefy, and a blank could or could not appear between E and fur. So here there's a blank between E and fur, right? Whereas here there isn't, and both are acceptable. However, when I have a repetition of a character, a blank must appear. I can have a do nothing at the beginning. I can also have a do nothing at the end. So that modifies my graph. The graph is now going to look like this. I can say that I can have a nothing in the beginning. I've changed my example. This is why I hate it. Now I wanted repeating characters. This just became beef. Okay. Anyway, so I can have a blank in the beginning and a blank at the end. Look at the and the graph itself ends up looking like this. It's somewhat more complex. So observe that the first character can now either be a blank or a B, right? B can be followed either by a blank or an E. That's what the arrow to the left shows. But then E must be followed by a blank because the next character is also an E. If I skip the blank, they would get compressed, right? And then the second E could be followed by either a blank or an F. So I can either go from the E to the F sequentially or skip the blank. And then the last F could be followed by a blank. So when I compose this graph, every arrow over here, you've got to assume that there's a direct sequence of arrows going through the symbols as well. So each of these arrows basically reflects one of the arrows on the left-hand side graph. So for example, you have an arrow going from E over here to F over here, which basically shows what's happening here, right? But you don't have an arrow going from, where is this? E over here to E over here. There's always an arrow from E to a blank. You don't have, okay, this is E, right? You don't have an arrow going from an E here, and it's not skipping three rows and going 3 down. So what is happening is, if you look at the arrows in the graph, you will find that from any row, I can either have a transition going to the next blank, or skipping the blank and going to the next symbol, unless the next symbol is the same as the current symbol, in which case I have to go through the blank. And then once I compose the graph in this manner, the rest of the algorithm is straightforward. I can just do my forward algorithm through this graph. The definition of predecessor has changed, that's all. Now some nodes will have 2 predecessors, some nodes will have 3 predecessors. I can also use the same graph, the modified graph, to perform the backward algorithm. Some nodes will have 2 predecessors, some will have 3. And then once I do that, I'm going to get alphas and betas going forward and backward. And the posteriors are going to be computed exactly the same as before, but using the extended graph with blanks. So the overall training procedure for sequence to sequence with blanks is given an input and output, given input and output sequences without alignment. If you want to train the model, you're going to set up the network, initialize all the parameters of the network, but now we're going to include the blank symbol in your vocabulary. And then subsequently, you're going to compute a probability for every symbol at each time. Then you're going to compose this graph, which also includes the blanks. And then you would perform your forward backward through this to compute the alpha and beta for every node in the graph. And finally, use those alphas and betas to compute your divergence and the derivatives. And this is what you'd use for backpropagation. So this overall framework that we just saw is what is called CTC. Yeah?
In this case, do we need to sum all the derivative of the blank in each row?
Yes, pretty much. Everything that we've done so far still holds. All that happened is that the manner in which you compose the graph changed. Yeah?
With this graph, you can also see that E blank would also be a value combination in the graph, but that would be wrong because that would mean something.
So over here, if you actually look at this, the graph is composed so that every path from the beginning to the end is necessarily a valid expansion of BE if. Right? I've changed my symbol sequence. Now I actually have two E's occurring one after the other. You will not have one. Take a look. Because if you want to have three E's, any paths are going from the top left to the bottom right. So once I hit the second E, there's no way for me to go to a blank and come back to an E. If I go from E to the blank, I have to go to the F. Right? So all the paths are restricted. Now, this thing is what is called the Connectionist Temporal classification framework. And this applies to models that are output order aligned but time asynchronous outputs. Now, I'm going to stop here because we're kind of out of time. But actually, let me go through this very quickly. It will take me a couple of minutes. Now, observe that once I have this kind of a model, I can perform a greedy decode, and I don't have to worry about the ambiguity of compressing sequences because a compression of a sequence is unique. Anytime I have a repetition of a symbol, there is going to be a blank between the two. Nonetheless, we did observe that the greedy decode actually finds the most likely symbol at each time, and this only finds the most likely time synchronous sequence. It's not necessarily the most likely order synchronous sequence. To give you an idea, here's an example where I have 6 possible time synchronous sequences. And their probabilities are listed. A greedy decode is going to pick TED because that has a probability of 0.71. But there are 3 different alignments of TED, and the 2 others have very low probability. Now the 3 alignments of red all have very similar probability, but they're all slightly below that of the best TED. In this case, which of the two sequences is a more reasonable decode, red or TED? Red, right? Because overall, across all possibilities, that is more likely. And a greedy decode is not going to pick that guy. Now, it turns out that greedy decode is actually, it still does a pretty good job because the manner in which this entire CTC framework is set up, it just turns out that because of the introduction of the blank symbol, a greedy decode will give you a pretty good decode most of the time. You could just implement a greedy decode, which is very easy. Just pick the most likely symbol at each time and compress it, and things will work. I won't explain this slide because I'm out of time, but what the authors showed over here, the original authors of this work, was that if you perform a greedy decode, the blank symbol actually is the most frequently occurring symbol and naturally consumes all the steady state portions of the input. From our problem, what we want is to find the compressed sequence that is most likely given the input. And how do you compute the probability of a compressed sequence given the input? The way we do it is to compose the graph and then find the alpha term at the bottom right of the graph, right? That is the only way in which you can compute the true probability of a compressed sequence. So if you want to find the most likely compressed sequence, you want to enumerate every possible order aligned sequence that you could have generated. Compute the alpha for every one of these, and then pick the one that is most likely. And clearly this is not going to be feasible. It's computationally impossible, right? And so, again, the actual objective of decoding is to identify the unaligned sequence that has the highest probability given the input. And this is the same as finding the compressed sequence with the highest alpha for the final symbol at the final input. And this is not a computationally feasible problem. So there is, of course, an engineering solution to this. So I'm going to take 1 minute extra. And the engineering solution is this. I can represent all of my order aligned sequences as a semi-tree. So here, for example, I am assuming a vocabulary of just 2 symbols, S1 and S2. So when I'm generating an order aligned sequence, the first symbol can be either a blank or an S1 or an S2. Then S1 can be followed either directly by an S2 or it can be followed by a blank and then followed by an S1, because if you want 2 repetitions of S1, it has to go through a blank. But then an S1 followed by a blank followed by an S2 is also valid. That's also an S1, S2, right? So if you look at this portion of the graph starting from S1 up there, that little portion gives you every way of generating S1, S2 and S1, S1, right? Similarly, the lower portion of the graph over here shows every way of generating S2, S1 or S2, S2. And so now you can just have repetitions of the same structure going forward all the way to infinity. And this is showing you every possible unaligned sequence with the appropriate, expressed as a tree, with the appropriate introduction of blanks to separate repetitions, right? And now here's what I would do. This figure to the left is the same as the tree over here. And now I can unroll this tree into a graph as we saw. So anytime there's an arrow between a node, every row in the graph represents one of the nodes in the tree. Every time there's an arrow between a node in the graph and another node at the next time instant, it means there's an arrow between those nodes in the tree. So what this means is that every single row over here represents a unique compressed sequence. And now I can just run my forward algorithm and compute alphas at every possible node at every possible time. And when I run out of time, I'm going to pick the alpha that had the highest value, and that's going to give me my compressed sequence, the most likely compressed sequence. Except, of course, this thing is going to blow up with time, right? So we do something called beam search, where we say I'm not going to let this structure grow to more than, say, 10 nodes at any time. And so you grow the tree one step, it will grow up, retain the best 10 nodes, and then take a step forward. So now that's going to grow a bit, retain the best 10 nodes, and repeat the process. And then you pick the best alphas. I'll stop right here. I've gone over it by 2 minutes. I apologize, but yeah. Thank you.